Today I want to talk about some work that Felisa and I have been doing together over the years since I started postdocing with her and Jim. Not actually still postdoc, but anyway, as a graduate student, I read this paper by Jim and Brian and was really struck by the idea behind macroecology and what basically they were saying here, in part because at the time I was in a paleontology program. And one of the frustrations that paleontologists have is trying to communicate with ecologists. And what Jim and Brian did, really, for paleontologists is give us a language that we can use to communicate with ecologists. The macroecological approach that they laid out is it's very applicable to fossil data. Both Jim and Brian followed up this paper with books more fully laying out the case for macroecology, pointing out all of the different consistent patterns that you see in macroecology and the potential mechanisms behind them. And I was really taken by a statement in Jim's book that pointed out that in this macro approach, long temporal scales were one of the approaches, or one of the areas that macroecology encompassed. And because of that, when it was time for me to think about postdocs, I went to Jim and said, Jim, I really want to do a postdoc with you, and basically what I want to do is Jim Brown through time. And fortunately, Jim understood what I was saying, and understood that what I wanted to do was look at macroecological patterns in the fossil record, and try and ask questions about whether they're consistent across time, and if there are dynamics in these patterns in the fossil record that can tell us something about the processes that underlie them. And so what I want to focus on in this particular talk are body size distributions at various different spatial scales, and what we can learn about them by looking in the mammal fossil record. So in 1991, Brown and Nicoletto published this paper on body size distributions, in which they pointed out that there's this non-random pattern of body size distributions, and that the shape of these distributions change with spatial scale, and that these patterns must be a result of patterns that, of processes, sorry, that operate at each scale on both ecological and evolutionary timescales. So at the continental level, they showed that in North America, the body size distributions of mammals were unimodal and right skewed, but that as you change spatial scale, the distributions become progressively flatter. So they're not completely flat at the regional scale, but they're flatter. And then you tend to get uniform distributions at the local scale. Later studies, this one done by Felisa and colleagues, but Pablo has also published papers on this, Doug House has published papers on this, for mammals anyway. Many people have published on them for other groups of organisms. But they found that these similarities these patterns are strikingly similar across the different continents. And that you get this despite the fact that there are very few species in common across the different continents. And I think across all continents there's only one, well, 3 of the continents, there's only one species in common. So clearly there are some evolutionary processes behind the development of these patterns. But what I wanted to know is how consistent are these body size distributions across time? It makes sense that if there are ecological and evolutionary processes underlying these distributions, that you would expect to see them in the fossil record. There's nothing that fundamentally different about Cenozoic mammals, the mammals over the last 65 million years, that would make you suggest that you wouldn't see these in the fossil record, except for the extinction of the Pleistocene megafauna. So as I think Pablo alluded to in his talk, there was an extinction of large mammals about 10,000 years ago in North and South America, 35,000 years ago in Australia, and 50,000 and 100,000 years ago in Europe and Asia. And on each of these continents, a substantial portion of the large-bodied fauna was removed. And so one obvious question then is, how does that change the overall continental body size distribution? And then what happens as you go down the spatial scales? Do you see these same patterns that Brown and Nicoletto found, or is at present warped, basically, by this extinction event. So the questions I'm going to address in this talk today are, how similar are the body size distributions across continents and large islands when you look across time? And then for local body size distributions, how consistent are they across time and space? So to do this, Felisa and colleagues put together this amazing database on mammal body sizes for all mammals of the globe for the late Quaternary. So most of what I'm going to be talking about is using this database. And I'll start with the first question. Okay, so this is the global body size distribution of mammals in the late Pleistocene. And you can see that there are striking similarities with what Brown and Nicoletto found. It is a right-skewed distribution. It's more multimodal. You do get a second mode of large-bodied mammals when you bring in the extinct Pleistocene things. But also, if you look at non-terrestrial mammals, if you put in the bats, you put in the aquatic mammals, you see that they too show this same characteristic pattern. It's truncated in the body size distribution, but again, you get these right-skewed distributions. So basically, the extinction adds in more large mammals and changes it from being more unimodal to multimodal. But this basic right-skewed distribution with a mode at about 100 grams is consistent in the late Pleistocene. When you look within the continents, when you break this down and look within the continents in the late Pleistocene, you again see the same thing. So the white bars are the body size distribution of the extant species, and then the black bars are adding in the extinct species. And what you can see is that in Eurasia and Africa, this extinction event was much less pronounced. And so you, all along, we've had this second mode of large-bodied mammals. When you add in the extinct species in North America and South America, you start to see distributions there that are much more like what you see in Africa and Eurasia. You get this second mode of large-bodied mammals. And if you look across the last 65 million years at these distributions, what you see is this bimodality in the distributions of having a mode of small-bodied species and a mode of large-bodied species has been pretty much the state of mammal body size distributions since about 40 million years ago. And this is coincident, basically, with about the time that the forests started retreating and the world became less warm and less tropical, and you got the spread of open spaces, basically. But since about 40 million years ago, you've seen this bimodality in body size distributions of mammals, and that didn't change until the end Pleistocene extinction. Now, if we change spatial scales just a little bit and look at large islands, what we actually see is, again, you see this size-biased extinction. Large mammals were affected to the exclusion of small mammals, or smaller mammals. But what you see are these flatter distributions, like Brown and Nicoletto showed at a regional scale. Basically, how peaked these distributions are is related to the area of the island, and the number of species on them. So Tasmania is one of the smallest islands shown here, and it has a much flatter, more uniform distribution than the other islands do. But what this does suggest is that this, the pattern that Brown and Nicoletto found for smaller spatial scales at a regional level is in fact consistent, and we do pick it up in the fossil record. Okay, so what about local body size distributions? We put together a database of local community species and added in the body sizes from the MOM database. We had about 300 fossil sites, most of them from the Holocene, about 90, well, exactly 92 from the late Pleistocene, and then another 300 or so sites across the globe in the present. And so what I'm going to talk about next is the shapes of these distributions in the late Pleistocene and Holocene of North America, and how that compares to what we see globally in the present. For the fossil data, it's taken from this database called FaunMap that you can find easily on the web. The fauna lists for the modern localities were taken from various literature and web sources. As I've already said, the body sizes came from the MOM database. Sites had to have at least 20 species in order to be included in the data set. For the modern sites, they had to cover less than 10,000 square kilometers, and only continental sites were used. Okay, so what I'm showing you here, the way that I'm going to be looking at local body size distributions is by comparing the moments of the distribution, the median, the skew, and the kurtosis. What I'm showing you here is a comparison of the median body sizes for all these communities for the late Pleistocene in red, the Holocene in yellow, and the modern, just North American communities in this case, in blue. And there's actually no significant differences in median body size, despite the fact that the late Pleistocene communities had the large-bodied mammals in them. Now, if you recall from Brown and Nicoletta, one of the things that they argued was that you get the turnover in these body size distributions at the local level, mostly in the small mammals, and that the large mammals had large geographic ranges and are occurring over and over again in the communities. And so this is consistent with that prediction. You do see some significant differences in skew among the different time periods. And in fact, the Pleistocene communities have a more positive skew than the Holocene, than do the modern communities. That's not that unexpected if you're adding in these large-bodied mammals. One way to increase skew is to pull out the tail of the distribution. And in the case of kurtosis, what we see is there are significant differences in between the fossil communities and the modern communities, but not between the late Pleistocene and the Holocene. But one thing to note from this is that although they are significantly different, the values of the kurtosis indicate that the late Pleistocene and Holocene communities are still relatively uniform. And if you look at the variation in the data, what you actually see is that the majority of the fossil communities have kurtosis values that fall within the same range as what we see in modern North America. There are about 60% of the communities fall within the same range. So clearly about 40% don't. And I think there's a couple of things probably going on. One is, we're talking about fossil data. It's inherently messy and sloppy. Some of these communities are going to be time averaged, which means that you're going to get more peak distributions because you're mixing groups of species that didn't actually occur together. So some of this variation is just due to the fact that I'm using fossil data. However, because of the expansion of the ice sheets, species were shifting around quite a bit in the late Pleistocene and the Holocene. And we do know that Pleistocene and Holocene communities were more rich than communities today because the species were displaced by the ice. And so some of this undoubtedly is real, and it's due to the addition of these extra species into these communities. All right, so how does this compare to what we see across the globe in the present? Well, if you look across the globe in the present, what we see is that there are significant differences among the different continents, and this is consistent with papers published by Pablo and by Doug Helt. In this case, we find that Africa is significantly different from pretty much the rest of the continents, and that South America is significantly different from Australia and Eurasia in terms of median body size. And what's actually going on is there's a latitudinal gradient in median body size in these communities, such that median community body size decreases as latitude increases. This is probably partly an artifact due to the fact that we've lost the large-bodied species in North America. This pattern would probably look a little bit different if we hadn't lost the large-bodied species. There's no significant differences in the skew among the different continents, but there are significant differences again in kurtosis. And in this case, North America is significantly different from the other continents. And again, South America is significantly different from Australia and Eurasia. And what this really seems to be is, again, there's a latitudinal gradient in the shapes of these distributions. But if you look at this, what really seems to be going on is that there is a temperate tropical difference. That is, in the communities in temperate latitudes, you tend to get kurtosis values that are consistent with having these relatively flat, uniform distributions described by Brown and Nicoletta. And you get a huge range of variation in the shapes of these distributions in the tropics. So you might think that it's climate, and if you just look at the relationship between these variables and mean annual rainfall and mean annual temperature, there is a relationship, but it's weak. If you look at habitat, I think this is where you see some explanatory power. For median, tropical forests and woodlands are significantly different. They're significantly larger body sizes. For skew, tropical forests and woodlands, again, are significantly different. And for kurtosis, tropical forests, again, are significantly different. And if you break this down and look at these data, again, as a function of habitat, what you basically see is that in deserts, you get these relatively flat distributions. In tropical forests is where you see all this variation. And it has to be something to do with both the three-dimensionality of forests and the productivity, because temperate forests don't show this huge amount of variation as well. So there are gross similarities in these macroecological patterns across space and time. Continental body size distributions have been bimodal for the last 40 million years, up until the end Pleistocene extinction. Shapes of local body size distributions differ across continents, but they're consistent within a continent across time. Shapes of local body size distributions seem to be related to habitat type, and in particular, tropical forests are showing more variation and more peaked distributions than other habitats. So what does this mean? Well, we can pick up these macroecological patterns in the fossil record. This gross similarity suggests that macroecological processes are important in macroevolution, and I think that's a message that we need to get out to the paleontologists. Discrepancies are probably a result of this anthropogenic extinction of the late Pleistocene megafauna, and we need to keep that in mind. As Ed pointed out in his talk, humans have been having an effect on communities, and we need to keep that in mind when doing ecology. And humans have been having an effect for a long time, a lot longer than we tend to think. So interpretation of present-day macroecological patterns should include consideration of